We can use titration for oxidation reduction reactions as well, known as redox titration. The difference is this time there is a transfer of electron from reducing agent to oxidizing agent. Now, a couple of oxidizing agents such as potassium permanganate, potassium dichromate, and one reducing agent, and then there are a couple of reactions that you're going to be exposed to, and there are possibility to be questions on paper 3 for you. So when we put potassium permanganate and we have iron 2 in the solution, iron 2 gets oxidized to iron 3, and once you see the purple solution showing up, then you know that's the end point, and we stop and we do our calculations. The same story with potassium dichromate, which is orange. If we add it to iron 2 plus, it gets oxidized to iron 3 plus, and chromium gets reduced to green color, and when the green shows up, we stop the reaction, and that's the end point. Now, why we are doing that? Because we want to get into dissolved oxygen and biological dissolved oxygen or biological oxygen demand. If the amount of biological oxygen demand is low, actually you have high amount of oxygen, low level of pollution, and we call that water pretty much healthy. On the other hand, if biological oxygen demand is high, that means you don't have enough oxygen dissolved and you have lots of pollution and the river is toxic. And we have gauges that they go parts per million. And we are going to do one calculation. The new syllabus has introduced back Wrinkler method, which is really outdated because we have probes that can measure oxygen. But this is a good practice of redox titration. So let's just look at reactions and equations involved. So in Wrinkler methods, you have manganese in an alkaline solution, and then acids, and then finally iodine with a starch complex is going to be the end point. So these are the reactions involved, and we are keeping track of oxygen. Usually we want to know how much oxygen you have dissolved in that solution. So if you follow this, 1 mole of oxygen becomes 2 MnO2, so 1 to 2 moles. Then the same MnO2 produces 4 moles of iodine, so it's a 2 to 4 moles. And then finally iodine needs 4 moles of iodine needs 4 moles of thiosulfate to reach its endpoint. And if you follow it, is 1 to 2, the 2 to 4 and 4 to 4, that means 1 mole of oxygen is proportional to 4 moles of iodine and needs 4 moles of thiosulfate. So eventually, this is the relationship that is important. Every 1 mole of oxygen requires 4 moles of thiosulfate. So we can use this information to sort of work backwards and tell you how much oxygen we have, if we have this information. Now let's look at a typical question that you will be exposed to. So Wrinkler method was used, and apparently they go after 100 centimeter cube of sample of water. They take that, and this is how much sodium thiosulfate was used in the process. So we have this information, and now what you have to recall is it's 1 to 4. So if I know moles of sodium thiosulfate, I can divide it by 4, and I know my moles of oxygen. And remember, moles is nothing but concentration times volume. So for thiosulfate, it's concentration times volume. Concentration is 5 times 10 to minus 3 mole per decimeter cube times volume. The volume is centimeter cube. We have to convert it to decimeter cube. So we divide it by 1,000, and when you do this, you find 8 times 10 to minus 5 moles of thiosulfate. Now remember, if you walk backwards, this will say for every 4 moles of this, you need 1 mole of oxygen. So in order to find moles of oxygen, I'm going to divide this number by 4. It's 1/4 of that, which is 2 times 10 to minus 5 moles of oxygen is in 100 centimeter cube of that sample of water. Now we are going to convert this to mass. Mass is nothing but moles times molar mass. So it's 2 times 10 to minus 5, multiply, it's diatomic oxygen, so 16 times 2 is 32. And when you do this, you will get 6.4 times 10 to minus 4 grams of oxygen. Now, usually the biological oxygen demand is expressed in milligrams per decimeter cube, that's parts per million. So first I'm going to convert this to milligrams by multiplying by 1000. So it is 6.4 times 10 to minus 1 milligram of oxygen. Now if you divide it by your sample, which was 100 centimeter cube, and that's 0.1 decimeter cube of water, this will turn into 6.4. So 6.4 parts per million is the amount of oxygen you have in your sample. So this type of calculation you are required to do, and it's simply following the coefficients mole to mole, and this is example of redox titration in its practice.